All right, Ivan, can you hear me okay?
Yes.
Awesome. All right, so let's get rolling. So quick announcement before we get started. So as a reminder, there was no mini quiz yesterday. There's just one on Sunday. So the homework and the mini quiz are on 5.3 and 5.4 that are due on Sunday. And then next week we have a mini quiz and a chapter quiz on Wednesday. So they're both on the same day. So keep that in mind for your planning. Also, the last day to submit any homework, if you're doing it past due for partial credit, is next week on Thursday. So keep that in mind if you're planning on doing that. All right, so we are going to pick up, we have one more example to do in section 5.3, and then we're going to switch over and start 5.4. So I'm going to switch over to the doc cam. And here's the example that we have left. So as a reminder, we were talking about area between curves, and you can see the example we did before, where we have these two functions, we're interested in the area between them. So here, example 7 says, suppose that the rate of oil production for a country can be modeled by Q of T equals negative 4T squared plus 35T plus 500 million barrels per year, where time T is in years since 2000. From 2000 to 2009, this country exported oil to the United States at a rate of R of T equals negative 2.5 T squared plus 20T plus 250 million barrels per year. So what do we want to do here? We want to graph both the oil production and the exportation on the same graph to see what they look like. B, if the rate of production and the rate of exportation continue at the same rate, do you expect demand of exportation to exceed production? So what does that mean? At some point, will the amount that is being exported exceed the amount that we can make, right? And if so, when does that happen? So you're going to look at the graph and see if you can figure out when that may occur. And then part C, find the area between the curves from 2001 to 2009, and what does this represent? Okay, so we're really thinking about how we set up these curves, how we think about the area between the curves, and how we interpret the findings that we're getting. So I'm going to give you about 3 minutes to try this out. On your calculator, on the graphing, when you do y equals, you have to put one of each of these functions in each of the y equals to graph them simultaneously. So try that out, see what you can come up with, and then in about 3 minutes, we'll go through it together. Okay, take about 30 more seconds. All right. So the trickiest part of this, I think, is trying to graph both of these together. So I did my best to sort of sketch what this graph is going to look like. And so here the production is the one on top, the QT, which was the negative 4t squared plus 35t plus 500 million barrels per year. And R of t, which is the red one, the one that's below, right? We have negative 2.5 t squared plus 20t plus 250 million barrels. So graphing it, you can see that the production, for most of the time it's graphed, is going to outweigh the export. It's going to be higher. Now, when we're talking about production and exportation, we're talking about what's happening starting in the year 2000, time equals 0. So that's here. So this is, we'll just put a 2000 there to remind us that that is the year 2000. And so we're really only considering what's happening on the right part of this graph, right? When you graph the functions, you get the whole thing. But contextually, it really only makes sense. This is our starting point. We're only considering things to the right of time equals 0. Okay, so part A is just to graph both of these on the same graph. So that's what we're looking at here. Part B says, if the rate of production and the rate of exportation continue at the same rate, do we expect the demand from the exportation to exceed production? And if so, when? So if we look at the graph, we can see that production, the rate of production, is exceeding exportation for most of the time. But when we come over here, this is where they switch. Okay. So at this point, the amount that is being demanded to be exported is higher than the amount of production. So it's at this point that exportation is going to exceed production. So in order to find that point, we would set these two functions equal to each other and solve if you're going to do it algebraically. But you can also do this if you have these graphed on a graphing calculator by using one of the functions on the calculator. So you use like the second calc button, and one of them is intersect, and you can find out where these intersect. And so if you do that, you see that this intersection point is 18 years after we started modeling. So that means in the year 2018 is when the demand of exportation is going to exceed the production level. Okay, so we're looking for this intersection point because that's when the other function is higher in terms of rate of change. Now for part C, what are we looking at here? Part C, we were asked to consider, where is part C? Oh, part C is right here. Part C, we're asked to consider the area between Q of T and R of T from 2001 to 2009. And we're asked, what does this represent? Okay, so 2001 is going to be a little after 1. And 2009, is roughly here. Right? So we're asked to find the area between these two curves. So we're going to use definite integrals, right, to set this up. So we have the integral from 1 to 9. So remember, time is in years since 2000. So in 2001, it's been 1 year until 2009. So between 1 and 9, that's what we're interested in. From last time, we found out that if we want to find the area between curves, we're going to do top curve minus bottom curve. So what does that look like here? So we have negative 4t squared plus 35t plus 500. That's our top curve. Minus, now again, you want to use parentheses because we have more than one term. So negative 2.5 t squared plus 20t plus 500 dt. Okay, and this is the bottom curve, which is our exportation. So if we find the area between curves, we would plug this into our calculator very, very carefully. And we would get 2,236. And the units here were in millions of barrels of this oil. So what does this represent, right? What does the area under the curve tell us about the situation? So remember that we are producing all the area under Q. We are exporting all the area under the R of T, or the red one, okay? And so that means that the area between the curves is the extra or the excess produced. So that's the amount that was not exported. So it might be used by whoever was drilling in their home country or something of that sort, but it's the excess or extra that was not exported because we produced it, we drilled it, but we didn't send it away, right? That's how much we have extra here. So that's what that means in that context. So you can kind of see why we would need to use these area between curves types of things to think about things where we have an influx of something, but we're also sending some of it away. The area between curves helps us understand how to evaluate and look at those types of things. Okay, so that is that example. We're going to shift now and we're going to go into the next section, which is 5.4. And 5.4 is going to look at what's called interpretation of the definite integral. And so what that means is we're going to be thinking about things like units and initial values when we consider talking about, right, our different various definite integrals. So let's start by thinking about how the notation helps us understand the units of the definite integral. So the units of measurement for a definite integral, so that's supposed to be a to b, it looks like a 0, from a to b of f of x dx is the product, so the multiplication of the units for f of x, so the units of the function, and the units of x, which is the independent variable that is sort of within this particular function. So there's sort of two scenarios that come up in this way. So the first is that the units of f of x and x are the same, right? And that happens occasionally. And if that's true, you end up with some sort of square units. So if the units of f of x are centimeters and x is centimeters, they're the same, then the units of the integral become centimeters squared, right? So if you have two of the same units, it becomes that unit squared. That happens not quite as often as our next scenario, which happens the majority of the time, where the units of f of x are some sort of ratio, c over d. So that might be miles per hour, feet per second, gallons per year, right? Something per something. And that's sort of commonly how we see it because we're looking under rates, and rates tend to have this something per something. When that happens, the units of x, the independent variable, are going to be the same as the units of the denominator, so of d. So these are going to be the same by design because, again, when you have a rate, it's the units of the dependent over the independent. Therefore, the independent units are going to be the same. So when that happens, when you have this rate, what ends up happening is that the units of the independent variable and the denominator of f of x are going to cancel, and you're going to be left with the units of the numerator. So for example, let's assume for a minute that the units of the function are in feet per minute. Okay, so maybe you're changing, maybe you're running, I don't know, 100 feet per minute. And so that means that your independent units are minutes. It's going to be the same. So if you look at the area under the curve here, you're going to be left with something in feet. So how much did your distance change in feet? So those minute units are going to cancel, and you'll just be left with the units of the numerator. This is the more common one that shakes out the second one where we start with a rate, but we'll see how this works when we look at some examples. So let's start with an example here. A bacteria colony initially has a population of 14 million bacteria. Suppose that t hours later, the population is growing at a rate of f of t equals 2 to the t million bacteria per hour, okay? So for part A, we want to have the definite integral that represents the total change in bacteria during the time from time equals 0 to time equals 2. So we just want to set up that definite integral. You can calculate it in part A. You don't have to, but we will need to for part B. For part B, we want to know what is the bacteria population at time equals 2. So we need to think about how much we started with, how much it changed, and for both, for A and B, if you're talking about any sort of number, you want to include units. Okay, so I want you to take 2 minutes, see if you can sketch those pieces out. Try that out, and then we will go through it together. Okay, take about 30 more seconds. Okay. So for part A, we're setting up an integral that represents the total change of bacteria. So if we want to know how much the bacteria population changes, we need to integrate the rate at which the bacteria is changing. So here we have an integral from 0 to 2. We're integrating our rate 2 to the t dt. And so this is the integral that's going to represent the total change from time equals 0 to time equals 2. You can either calculate this in part A or part B, doesn't really matter. But when we plug this into the calculator, we're going to get 4.328. And when we think about the units of 2 to the t are in million bacteria per hour. Just going to abbreviate because I've lost space, million bacteria per hour. And then the independent units are going to be hours, right? It's going to be the same when you have a per something. So when those cancel, we get 4.328 million bacteria. Okay, so that's how much we've changed. Now, part B wants to know what is the population at time equals 2. Well, in order to answer that question, we need to bring in the fact that when we started, that the initial population was 14 million. So we had 14 million, then we changed by 4.328 million bacteria. So that means that the total population is 18,328 bacteria. So million bacteria. So we have to read the question carefully and notice that we do have a starting amount and understand that the definite integral tells us how much that amount changes. And so here we get a total population of 18.328 million bacteria. Okay, so that's one example of how we're going to be using our units and thinking about this. We're going to look at two questions together next. So one is computational and one is not. So for example 2, suppose that C of T represents dollars per day to heat your home, where T is time measured in days and T equals 0 corresponds to January 1st, 2018. Interpret 0 to 90 C of T dt. So what does that mean? So we're asking what this integral represents. So you can't actually calculate anything here because we don't know the function for C of T. We're asking what does it represent? So the 0 to 90, once you calculate it, what are the units going to be? What does that tell you? So we're really looking for a sentence here that describes what's happening in this integral. For example 3, we have water is being pumped out of a holding tank at a rate of 5 minus 4e to the negative 0.15 t liters per minute, where t is in minutes since the pump started. If the holding tank contains 1,000 liters of water when the pump is started, how much water does it hold 1 hour later? So if we have the rate at which water is being pumped out, we can figure out how much is pumped out over that first hour and use that in conjunction with the other information to understand how much is in the tank after that 1 hour period. For that one, we are going to do calculations. Be really careful with units and how you set that up, and think about how you are interpreting your answer and if it makes sense in this context. Okay, so I'm going to give you about 3 minutes to do these two problems, try them out, and then we will go through them together. Okay, take about 30 more seconds. All right. So for example 2, we're trying to interpret what's going on. So usually when we do that, we want to think about what the numbers on the integral are telling us. So 0 to 90, those are our independent values, where here we see that time is measured in days. So this represents 90 days, okay, in some sort of context. Now let's look at the units of our function and the independent variable. So C of T is dollars per day to heat your home. So dollars per day. And then the independent variable is day. So the day units are going to cancel. So when we integrate this, we're talking about the total dollars over 90 days. What 90 days? The first 90 days of 2018. So we're talking about the total cost, that's how we talk about dollars, to heat your home during the first 90 days of 2018. And of course, this is just one way you can write a sentence to represent this. The key things that you want to have here is that we're talking about 90 days, specifically the first 90 days of 2018. And we're talking about the cost or the number of dollars to heat your home over that time period. So your sentence may not look exactly like mine, but if it has the same elements with the numbers with the right units, then you're in good shape. Okay. So example 3, we're talking about water being pumped out of a tank at this particular rate, and we want to know how much is left after some period of time. So if we're trying to figure out how much was pumped out, we need to set up a definite integral with this particular function to see the total amount of water over this time period. So we have 5 minus 4e to the negative 0.15 t dt. Now, what are our bounds here? So we are told that time is in minutes, which means that our bounds need to be in minutes. So this says how much water does it hold 1 hour later? Well, we have to remember that 1 hour is 60 minutes. So the units on your bounds have to be the same as the units of your variable. So here, that was a little tricky. We're going to go from 0 to 60. So maybe you picked up on that, maybe you didn't. But if you didn't, write a little note to make sure that those units are going to agree. Okay. So when we integrate that on our calculator, we're going to get 273.336. And so we need to know what the units are so we can talk about what this number means and then go on to answer the question. So the units of our function here are in liters per minute. And our independent units are in minutes. So the minutes are going to cancel, which means that this is talking about 273.336 liters of water. Okay. Now, what do we do with that information? Well, we're told that the tank is containing 1,000 liters of water when the pump is started. What's tricky here is that we are told that this is the amount that is pumped out. So if we started with 1,000 liters and we pumped out 273 liters, we need to subtract that number from 1,000 to see how much is left. So we have 1,000 minus 273.336, which would give you 726.66 liters. Now, part of the reason why this is especially tricky is because usually when something is decreasing, your rate is negative. But here, the way that it's structured is that this rate represents how much has been pumped out, which is a positive value. And then we have to think about that in the context of the question. So if we read the question before we had done any math work, we'd say, okay, I started with 1,000 liters. I'm pumping some out. So my solution should be less than 1,000, right? So if we can think about that, that'll help us realize that we need to subtract that amount off. Okay, so that one's a little tricky. A couple of things that we need to notice here. So example 4 is another one where you're going to be writing a sentence to talk about what something represents. So the function f of t gives the number of gallons of fuel used per minute by a jet plane, t minutes into a flight. The integral from 0 to 30 f of t dt represents. So we're coming up with, what does this integral mean? Okay, so take about 1.5 minutes, 2 minutes, think about the numbers, think about the units, and think about a sentence that will represent what this definite integral tells us. Okay, so take about 1.5 minutes, and then we will go through it together. Okay, take about 30 more seconds. Okay, so again, I usually like to start by looking at the numbers that are on the integral, right? Because that's one of the 2 pieces of information we need. So here we're talking about 0 to 30. So the first 30 something, right? So if we look at the independent variable, it's the first 30 minutes. Okay, so we're talking about a 30-minute time span. And so what is happening over these 30 minutes, right? So f of t, the function that we're evaluating, is gallons per minute of fuel. And then the units of the independent variable are minutes. So whatever this is, whatever this number is, it's in gallons, right? So gallons of fuel. So a sentence that we could write would be something like, the total number of gallons of fuel used during the first 30 minutes of a jet flight, something like that. Right, so we're talking about gallons of fuel, and we're talking about how much is used during this 30-minute chunk of this flight. We're just talking about the first 30 minutes because it's 0 to 30, so at time equals 0, that's when we sort of start everything. But again, the key things is that we're talking about 30 minutes and we're talking about gallons of fuel. So those are the 2 key things that we want to have in our sentence. Okay. So the next example that we're going to look at here, we're going to be doing some evaluation of some things, going back to thinking about what we've learned throughout chapter 5 and seeing if we can make sense of it in this context. So the rates of growth of the population of 2 species of plants, so we have species 1 and species 2, and these are the rates of change, measured in new plants per year are shown in the graph below. Assume that the population of the two species is equal at time equals 0. So time equals 0, however many there were to start, was the same for species 1 and 2. Question A, which population is larger after 1 year? So we're looking at these rates of change graphs and thinking about how we would evaluate them to think about the total population after 1 year, but then also after 2 years. And then part B, how much does the population of species 1 increase during the first 2 years? So we're trying to approximate more precisely how much it changes over those 2 years. We're not going to get an exact value on this, right? We're trying to estimate in some sort of meaningful way. There's a couple different ways that could happen. Think about what might be a good way to do this, but we're considering the first 2 years. So I'm going to give you about 2 minutes to think about this, think about how we would talk about these, how we would determine this, and then we will go through it together. Okay, take about 30 more seconds. Okay. So for part A, when we're considering which population is larger after 1 year, we're considering area under the curve because the area under the curve tells us how much the original population changed. So for species 2, at time equals 1, the area that represents how much the species changed looks like this. Whereas for species 1, the area under the curve is quite a bit bigger, which means that after 1 year, species 1 had a larger increase since there's more area under the curve. Okay, but when we look out to 2 years, right? So 2 is just about here. We're comparing this area, which got much, much bigger between years 1 and 2, to species 1, which is this area here. And you can see that the extra area from year 0 to 1 for species 1 is not as big as the extra area for species 2. So over the 2-year span, species 2 ends up increasing more, right? Because of that huge growth between 1 and 2. So again, when we're talking about the rate of a function, we need to look at area under the curve to talk about the change in the actual population. For part B, it says how much does the population of species 1 increase during the first 2 years? So now we're trying to approximate the area under this curve. There's a couple ways you can do it. You can find the area of one little block and then try to count how many blocks there are. To me, this looks pretty triangular. So I'm going to turn this into a triangle and use 1/2 base times height to approximate this area. So I'm going to try to draw this line darker so you can kind of see. Hopefully you kind of see that, right? So here, right, if you think about this is species 1 here. So if I do a triangle here, it's going to be a slight underestimate because I won't have this little area here. Okay, so if I do that, I have 1/2 base. Now my height is right halfway between 3,000 and 1,500, so 2,250. And that gives me an approximation of 2,250. And I know that that is an underestimate because I see this extra area here. I could try to approximate that extra area. I don't know that it's all that worth it to do. So just, if I'm looking at answers and one of them is like 2,300, that's probably reasonable, right? Whereas 6,000 is going to be way too high of an estimate. I can come up with a pretty easy overestimate by doing a rectangle for species 1, right? So my overestimate would be like this whole rectangle, which is way too big. And that would just be base times height. So 2 times 2,250, which is going to give me 4,500. So I think the triangle is a better estimate. It's closer to the actual shape. So somewhere, 22 to 2,500, I think is a pretty reasonable approximation. So that's how I approximated it. But again, you could find, the area of one block and then try to count the number of blocks. That works too. Okay. So again, these are approximations, they're not exact. So we're doing the best we have with the tools that we know. So the next examples that we're going to look at have to do what's called the bioavailability of drugs. And this is related to surge functions, which we learned about and talked about in section 4.8. 4.8 a couple weeks ago. So just as a reminder, a surge function is a function that measures the amount of medicine in your blood at any given time. And it has this particular shape. We usually use C of T for concentration. So the bioavailability is related directly to surge functions. So in pharmacology, we use the definite integral to measure the overall exposure of a person to a drug during a course of treatment. So what that looks like is finding the area underneath the concentration curve to help determine what's called the bioavailability, which is the total exposure. So there's certain drugs that over time, you can only have so much exposure before it starts to impact your organs or things like that. So that helps us sort of understand how many courses of a treatment you should get, things like antibiotics or cancer drugs or things like that. How many times you can take it before you have to switch to a new drug. If you've ever experienced antibiotic resistance, that this is sort of related. There's only so much time you can be exposed to a particular antibiotic before your body develops a resistance, and then you have to go to another antibiotic. So that has to do with the bioavailability. So when we are thinking about these, we're thinking about two different sets of things. And so the first one that we're going to talk about has to do with the absorption. So for the example we're going to look at, we're going to say 2 drugs are given to a patient and their concentrations are measured over time. And the question is, which drug was absorbed most rapidly? So what you're going to be doing is you're going to be looking at this picture with drug A and drug B, which is giving you the concentration of the drug in the bloodstream. And we're trying to figure out which is absorbed most rapidly. So okay, so we don't have a definition for that yet. We're going to build the definition from this problem. So what I really want you to do is look at the picture, use your critical thinking skills, think about what you see for these 2 surge functions, and think about how we would make a case for which one is absorbed most rapidly. See if you can figure it out and justify it in some way and write a sentence to justify your answer. I'm going to give you a minute and a half to try to think about this, think it through, think about your reasoning, and then we'll go through it. Okay, take about 30 more seconds. Okay. So how do we reason through which one is absorbed most rapidly? So remember that this particular function is talking about the amount of drug in the bloodstream. So we're asking which one is entering the bloodstream fastest, and then, secondarily, which one's going to peak first, right? It's going to peak first because it was absorbed faster. So which one reaches its peak first? So we're looking at this rate, and what we see is that drug A has a very steep incline. So that means that it's being absorbed very, very quickly in the beginning and reaches its peak well before drug B reaches its peak. So what we're comparing is how quickly we get to this peak, because that's how quickly we are absorbing it. And we also see secondarily that drug A dissolves out of the body faster than drug B because it was absorbed so quickly. So the way we want to think about this is in terms of the peaks. Which one rises to its peak the fastest? That means it's being absorbed more rapidly. So here, drug A is absorbed fastest, more rapidly, anything that indicates speed here. Okay, so it's going to be drug A. And again, it's because the rate at which we are reaching our peak is significantly faster than drug B, which is taking a little more time. You see the rate's not quite as steep as for drug A. Okay, so when we're talking about absorption, that's what we're looking at. We're looking at this steepness and which one reaches its peak first. For the next example, we're going to bring in this idea of rapid absorption, but also now pair it with this definition of bioavailability. So let's assume 2 products are being tested for pain relief. The graphs of both products are given below. We want to use these graphs to determine which drug works the fastest. So that is the same as the question we just looked at, which one is absorbed faster, and which drug has the largest bioavailability or overall exposure. So that brings in that definition of bioavailability. So take a look at the picture. Again, this is the concentration of product A drug and product B drug. Take 2 minutes, see if you can figure out, again, there's two questions here, which one works fastest and which one has the largest bioavailability. So pick your product for each one and then write a brief sentence about why that's true. Okay, so take 2 minutes and then we'll go through it together. Okay, take about 30 more seconds. All right, so again, there's two separate questions we're addressing here. The first one being which drug works the fastest, right? So which one's going to give you whatever the effect is quickest. And so that has to do with absorption and how quickly it's getting into the bloodstream. So again, when we look and compare these two, we see that product A is absorbed faster and reaches its peak quicker, right? So that means that the drug that works the fastest is going to be product A. Okay, so again, if we're considering, which one becomes effective first, which one's absorbed the fastest, that's all the same thing and has to do with the rate at which we are absorbing things into the bloodstream. The second question, which drug has the largest bioavailability? So how much is giving you the most exposure to the drug over time? We're comparing the areas under the curve. So here, product A, if we're talking about the area under the curve, is this area here. And we're comparing that to product B, which has this area here. And so what we see is that there's certainly more area under the product B curve over the time that we see this graph than product A. So that means it has a greater bioavailability, which means that the person is exposed to the drug for a longer and greater period of time than product A. Okay, so again, absorption, we're comparing the rate and the peak, and bioavailability, we're comparing area under the curve. Okay, so that's our last example for 5.4. We're not going to start 5.5 today, so we'll finish here. You can use your extra couple of minutes to enjoy some sunshine today or work on the homework, whatever works best for you. But we will finish up on Tuesday with the last section, which is 5.5. So have a great rest of your day, and I will see you all on Tuesday.